Dear colleagues, before we discussed an example in which we consider the transportation problem when the total production equals 30, total demand is also 30. So, and such a problem we call balanced. And for such a transportation problem, which is balanced, we constructed a mathematical model of the following form. And so in this case, when the problem is balanced, we use equalities for our restrictions. But in many cases in practice, such a property of balance does not take place. So for instance, we produce more in total than our customers need in total, or we produce less and it is the deficit and then our customers need. So in this case we cannot use this mathematical model, because when we produce more than our customers need, so we cannot guarantee such inequalities that we take all the units produced at each supplier. So obviously, if we produce more, if there is overproduction than our customers need, so it means that there will be a surplus on some suppliers' sides. So, and the question is, if the problem is unbalanced, what are the ways to solve such a problem? To resume, we may say that balanced models are the following. So the left-hand side is the following. So it is just a sum of a small 1, a small 2, and so on, a small m. So it is the total production. We may write down here, it is the total production volume. And if we consider the right-hand side here, so we can see that it is b small 1, b small 2, and so on, b small n. So it is the total demand. It is the total demand. And if the total production, so we may write down here, so when we have constructed a network, so we may check a balance right here. So here we draw a line and we summarize a small 1 plus a small 2 plus and so on, a small m. So we may calculate this volume, the sum of a smalls. And also we may draw a line here and we may calculate b small 1 plus b small 2 plus and so on, b small n, and calculate the right hand side here, total demand. So, and it is the sum of bij's when j runs from unit till n. And when there is equality, we should check it. So, and when there is equality, we answer yes, there is equality. So the problem is balanced. And in this case, our transportation problem has a solution. But when, balance condition, if the balance condition takes place, so then transportation problem has a solution. So, and let's consider special cases when there is no balance condition. What should we do? So here we may write down, if the balance condition takes place, then if and only if the balance condition takes place. So the transportation problem has a solution. Of course, when we consider all the ages from all the suppliers to all the customers, of course. So, and when we consider unbalanced models, so the first case for unbalanced models is, look, the sum of a smalls of productions is bigger than the total demand. So the right hand side it is the demand and the left hand side it is the production, and our production exceeds the total demand. So in this case It is the case of overproduction. So, what should we do in this case? When we have found that in this case we have overproduction. So let's consider the transportation table, and here let us calculate the total production. 11, it is the production of the first supplier, plus 11, it is 22, plus 8, so it is 30. And let us calculate the total demand. 5 plus 8, it is 13, plus 8 is 21, plus 7 is 28. So we can see that total production exceeds the total demand. So what should we do? If we produce in sum 30 choco boxes, but our customers need only 28 choco boxes, obviously that the surplus is 2 choco boxes, and in this case 2 choco boxes will be left on the first side, or maybe on the second side, or maybe on the third side, or maybe in some combination. For instance, 1 choco box at the first side and 1 choco box at the second side. So what is the way how to construct a mathematical model? So when we look at the mathematical model here, once again, so we the question is, do we guarantee that when we have an overproduction case, when we produce more than our customers need, can we guarantee that that equality is here and all the customers will get the demand? The answer is yes. Of course, if we produce 30 choco boxes in sum, but our customers need only 28 choco boxes in sum, we may guarantee that we will satisfy the demand of our customers and it will be equality here. We may guarantee this. But may we guarantee that we may take all totally, completely production volumes at each production places? The answer is no. We cannot guarantee that we will take all the produced amount, because we produce more than our customers need. So it means that the first way how to solve the unbalanced problem in the overproduction case, it is to change mathematical model. For the production places, we change such equality with inequality. So we change these equalities with the sign less or equal. So for overproduction case, because we cannot guarantee that we will take all the volumes. We may say that we will take A smalls or less than A smalls. And as a result, the first way how to solve overproduction case is to change mathematical model. So we need to change math model. How to change this? So we should change the restriction. So the only one point of the mathematical model, we change the restriction for our producers, for our suppliers. Xij less or equal than AI. And we should write this for all the production or supply sites. So I runs from unit till M. It is the first way how to solve overproduction case. But in this case, we let Excel to decide which supplier will have a surplus after optimization. But when there are penalties for keeping surplus at our suppliers' places, so we need to formulate a new model which is balanced. Formulate a new balanced model. So for this reason, we should consider a fictitious consumer. So how to do this? So consider fictitious consumer. So let's look at this table. We see that our production is the difference between 30 and 28. So we add a fictitious consumer. So consumers or customers are usually the columns in this table. So, and for fictitious guy, we need to add additional column. And the difference here is 30 minus 28, so demand here is 2 units. This is the first real customer, it is the second customer, the third, and the fourth. And of course, here we need to consider fictitious customer, and his number is 5. And here we consider C15. It is the fines or penalty for extra chocobox which we leave under optimization on their first supplier place. And so it is C25 and it is C35. So all of them are penalties for the first supplier, for the second, and for the third one. And if we consider a network, so it means that on the beginning, so we have 3 suppliers and we have 4 customers. And supply volume for the first supplier is 11, for the second one 11, for the last one is 8, and for the first customer demand is 5, for the second 8, 8 for the third, 7 for the last one. And we may calculate their balance. So 11 plus 11 plus 8 is 30, and 5 plus 8 plus 8 plus 7 is 28. So the problem is unbalanced, and it means that we add a fictitious customer. So it means it is the customer 1, 2, 3, 4, 5. It is the customer number 5 with demand 2, and if we consider for the first age 1, 1, marginal transportation cost from the first city to the first customer. So, but when we consider the age from the first supplier to our fictitious customer, so here we consider such a penalty C15 for extra chocobox which we leave here at this point after optimization. So, and the same fashion, we may consider these penalties from the second supplier, C25, and from the last supplier, C35. And as a result, we see that when we consider a fictitious customer, so when we summarize, the total demand is now 30 and problem is balanced. So we see that after such a formulation of a new balanced model, so we have a balance in the case, and we may continue with solving this problem and assume that we found an optimal solution, and assume that this case, for this fictitious customer, we found that a certain amount, for instance 2 units, appears in this cell. So x15 equals 2. So on this age there is 2 units here. So we deliver, it seems that we deliver from the first supplier to the fifth customer 2 boxes of chocolate. But the fifth customer is fictitious one. What does it mean, these 2 choco boxes? What should we do with these choco boxes in reality? So we cannot deliver two checker boxes to fictitious customer, obviously. But what should we do with these two checker boxes in real case? So it means that we keep these two checker boxes at the first supplier's warehouse. So after optimization, we take all the volumes from the second supplier and deliver them to real customers, and that's 0 here. And we take all these 8 choco boxes from the third supplier and deliver them to all the real customers. And only for the first supplier, Excel proposes such a solution in which there are 2 choco boxes from the first supplier to the fictitious customer B. So it means that we leave 2 choco boxes after optimization at the first warehouse. And of course, we should pay penalties for keeping 2 extra choco boxes after optimization at this warehouse. We should consider penalty C15 and multiply them by 2, because we keep 2 choco boxes here, and the result is the following. We have optimized all the system, and we have minimized the total cost, which include transportation cost from real suppliers to real customers, and also which include such a cost which are associated with penalties when we leave choco boxes, extra 2 choco boxes on the warehouses of our suppliers. And we have found an optimal solution to this whole system, and it is optimal to leave 2 choco boxes on the first supplier production place. As a result, the number of our fictitious customer is the following. So it is B capital N plus 1, because in the original problem there were N customers, and now there is a customer, fictitious customer, N plus 1. So as in our case, so in the original problem it was 4, so N was 4, but we consider the fictitious customer, one more customer, so B5. So N plus 1 is 5 in our case. So, and let's consider what is the demand for our fictitious customer. B small N plus 1, it is the total production, so it is the sum of I small when I runs from unit till M minus the sum of BJ's when J runs from unit till N. So in our case it was 30 minus 28, and the result was 2. So the result was 2. And we also should consider fictitious cost. Fictitious cost is C from the supplier number I to their customer number N plus 1, to the fictitious guy. And it is the fine or penalty for leaving 1 extra unit of our product at the place of the supplier number I. So, to resume, when we meet overproduction case for a transportation problem, we should first of all understand, are there penalties for leaving 1 unit of our product at the warehouses of our suppliers? If there are no penalties, we may take the first approach and just change a mathematical model. We change equalities for inequalities for supply sides, for the restrictions for the supply sides. If there are penalties, so for leaving extra production units at our suppliers, so we should consider the second approach, and we should formulate a new balanced model in which there is a fictitious customer, and this model is balanced. The second case is shortage. So when we consider the total production volumes and when we consider the total demand and the total production is less than total demand, so it is the shortage case. In this case, let's consider an example in which, once again, there is the first supplier which produces 9, the second produces 9, the next produces 8. So 9 plus 9, it is 18, plus 8, it is 26. And the demands are the following. 5 plus 9, so it is 14, plus 9 it is 23, plus 7 it is 30. And as we can see, it is the shortage case, so we produce less than our customers need. And in this case, the same fashion, the first approach we use when there is no penalties for unsatisfied demand. If there is no penalties for unsatisfied demand, we may go back to our mathematical problem. And the first question is, when we find a solution, do we take all the production units from our supply sites? Let's look at this example. So we produce only 26 and our customers need 30. So let's visualize such a case. So it is the first producer and the production volume is 9. The second producer, the production volume is 9. The third producer and the production volume is 8. And our customers, the first one with the demand 5, the second with the demand 9, the third with the demand 9, and the fourth with the demand 7. So let us calculate the balance. The total production is 26 and the total demand is 30. And we see that there is shortage. And the question is, when we try to satisfy the demand as maximum as possible, do we leave something? Do we have a surplus after the satisfactory demand on our supply sides? The answer is no, because we have not enough choco boxes to meet all the demand. And of course, we should take all of these production volumes and to meet as maximum demand as possible. So, and if we go back to our mathematical model, it means that we take totally, completely all the production volumes from our supply sides. So in shortage case, equality remains here, but we do not meet all the demand. And we cannot guarantee equality in the group of restriction for our customers. So this case is not guaranteed. And for shortage case, we should right here change our mathematical model, and instead of equality, we should write inequality here. So it is for shortage case. So when there is a shortage case, so equality is here for production sides and inequality is for demand sides. And so I may just hide this change, and for shortage case, so this is the mathematical model. When we minimize our objective function, there is equalities for the supply sides and inequalities for demand sides. When we consider the overproduction case, so I hide such a change in mathematical model, and in the overproduction case, we change equality on inequality for the production sides, and we keep equalities for the demand sides. As a result, for the shortage case, the first approach, when we have no penalties for unsatisfied demand, we change mathematical model, and we change only one group of restrictions for our demand sides. So I runs from unit till m, xij is less or equal than bj, and we should do such a change for all the demand volumes from the first one till the last one, number n. And if we do have penalties for unsatisfactory demand, so we should consider the fictitious supplier. So once again, so the same fashion, consider fictitious supplier. And if we look at the network, it means that we add a fictitious supplier number 4, and the supply volume is the difference between 30 and 26, it is 4. And if we consider the corresponding table, so we should consider the first row for the first supplier, the second row for the second supplier, for the third one, and for the fictitious supplier, so number 4. And here, once again, we consider such places for penalties. So, for instance, if we deliver from the first supplier to the first customer 1 Chocobox, we should pay C11. But when we deliver from fictitious supplier to first customer, we consider C for 1. So it is the penalty for unsatisfactory demand for the customer 1 of 1 unit of our product. So C for 1, C for 2, for 3, 4 and 4. And here the supply volume for the supplier number 4 is 4. And fictitious supplier is number m plus 1, and the supply volume for this guy is the difference between the sum of bj's when j runs from unit till n, so this is the same right hand side, minus the sum for I runs from unit till m of a small I, so it is the left hand side. And in this case also our fictitious cost are the following: Cm plus 1 comma j. So it is the penalties for unsatisfactory demand of 1 unit of our product for the customer number j. And when we have balanced our problem, so we see that now the total supply volume is 30, which is equals to our demand. Now we may continue with solving this problem with Excel and assume that we found a solution in which, for instance, there are 4 Chocoboxes here. So our fictitious supplier delivers 4 Chocoboxes to our customer number 1. It is X for 1. What does it mean? How we may explain this volume? Because this is the fictitious supplier. We do not produce 4 Chocoboxes at this place, but our solution is the following: we deliver from the fictitious supplier 4 Chocoboxes to our first customer. The interpretation is the following: we do not deliver 4 Chocoboxes to our first customer. So we meet the demand of the second customer totally, of the third customer totally, of the fourth customer totally. But there are 4 Chocoboxes of unsatisfied demand of the first customer. So it means that this guy needs 5 choco boxes. 4 choco boxes we do not deliver to him, so we deliver to him only 1 choco boxes. Of course, this customer calls us and say, where are my 4 choco boxes? We say, sorry, we have a shortage case. So our customer says, you will pay penalties for them. We answer, yes, we are ready. And we pay, of course, these penalties, but we do know that we have found such a solution which minimizes the total transportation cost and penalty cost. As a result, now we understand how to construct a mathematical model for the case when there is a balance, and also we may construct a mathematical model when there is overproduction and when there is a shortage. So, and now we may continue with solution of transportation problem. We will consider a special example, and we will run all these steps for a special case for a transportation problem during our computer class. And now, before we continue with computer solution, I would like to consider heuristic solution. So, heuristic solution could be used here, for instance, when we have no computer. So when we have constructed a network, or when we have constructed a mathematical model, so we may use a heuristic solution. And let's consider what does it mean, heuristic solution. What does it mean, heuristic solutions or heuristic methods? So we may say that heuristic methods or heuristic solutions, they are reasonable solutions or reasonable methods in some sense. And we will discuss what does it mean, a reasonable solution. And let's consider strengths and weaknesses. So when we speak about strengths, I may say that heuristic solution, they are simple and they do not require computers. Of course, we may run heuristic solution on computer, but we may find solution without computer also if we use heuristic methods. So it is strengths of such methods, but also we have weaknesses of such a method. So the weakness is the following. So this method do not guarantee optimality. So this method do not guarantee optimality. Let's consider the first method, which is known as north-west element. So because, why do we use such a title? So because north usually on the map is on the top, and west is on the left side of the map, and the idea, as a result, the idea is following. So in the table, we always fill the upper left cell. Always fill the upper left cell. So, and the implementation, we use the northwest element approach only to find a feasible solution. Let us consider how to implement north-west element approach, and we consider a model which we already seen today, and I will use the method northwest element to find a feasible solution for this case. And the first of all, we should find upper left cell in the table. Where is it? It is here. So to mark the number of step, I will use such a form. So it is the first step, and first cell I feel is this one, and the supply is 11, demand is 5. So how many choco boxes should I deliver? I deliver 5. because these guys do not need 11 choco boxes, they need only 5, so I choose minimum from 11 and 5, and minimum is 5. Now, demand for the first customer is satisfied, so the remaining demand is 0, and I correct the demand and also I correct the supply. 11 minus 5, so the answer is 6. So the new supply volume for the first supplier is 6, because I already taken 5 choco boxes from this 11, and it remains only 6 choco boxes. Okay, so the first customer now is totally, completely in chocolate, and he does not need anymore, and that's why he sends a message to the second and third suppliers. So I do not need chocolate from the second supplier. I do not need chocolate from the last supplier. So, and let's continue with the next step. Now, assume that there is no first column in this table, and we continue with the new small table. And what is the next step? What is the upper left cell in this case? So it is here, and it is the second step, and we fill this cell with the shipment volume. So remaining supply is 6 for the first supplier, and demand is 9. So, and we once again choose the minimum from 6 and 9, so and minimum is 6, and we write down 6 here. And now the first supplier is empty. He has no more chocolate, so it means he cannot send something to the customer number 3 and customer number 4, so zeros are here. And now the remaining supply is 0 for the first supplier, and the remaining demand for the second customer is 9 minus 6, it is 3. So, and the same fashion, we may see that now the new table consists only of this part of our table. So, and we continue with the same rule. What is the upper left cell here? Upper left cell here is this one, and it is the third step. We deliver here once again minimum from 11 and 3, minimum is 3, correct our demand is 0, and 0 is here, that's why we do not need more chocolate, and 11 minus 3 is 8, and this is the new supply volume. Let's continue, and in the Romanian table the next upper left cell is this one, and it is the fourth step, and we choose the minimum from 8 and 9, so minimum is 8, so correct here, it is 0, and 0 goes here, and now instead of 9 the remaining demand is 1, and the next upper left cell in the remaining table is this one, it is the step number 5, and we deliver the minimum from 1 and 8, and this is 1, and we correct our demand, it is 0 now, and we correct our supply, now it is 8 minus 1, it is 7, and now the last cell, which is the unique one, it is this one, and we deliver the 7 boxes of chocolate, and we correct our supply and demand. That's it. We take all the production volumes from our supply sides, and we satisfy all the demand. And the question is it possible to use north-west element approach for unbalanced problem? The answer is yes. So we will use the same method, and if the problem is the case for overproduction, so in a certain supply side we will have a surplus. If there is a shortage, so we will get in a certain place or certain places for customers unsatisfactory demand, but it is not a barrier for using of the northwest element approach. So now what remains here? We should calculate our cost. So it is the first one, the cost for the first approach, for northwest element approach. How to calculate transportation cost? 5 times 7 plus 6 times 8 plus and so on for all the rest cells. So I just consider the last one, plus 7 times 2. And if we find this value, so it is 150. I know the optimal solution for this case, and I know the optimal transportation plan, and I know that Z star, so the total transportation cost for the optimal transportation plan is 89. I just know. So, and we may compare that the difference is rather big. So, but nevertheless, we use northwest element approach only when we need to find a feasible solution, and we do not think about the costs. Yes, in reality, such a problem appears also, and we just need to find a feasible solution. And yes, in this case, northwest element approach works. Also, I should say that there is a finite number of suppliers, there is a finite number of customers, and in some transportation problem, northwest element approach is lucky, and in some cases, northwest element approach brings the optimal solution, but not in this case. The next heuristic method is known as least cost method. So the idea is the following. We always fill the cell with minimum cost. Implementation. To find a feasible solution, and also for estimation. For estimation, because now we take into account transportation cost, and this method allows us to somehow to estimate the transportation cost. This method seems like an optimal one because it looks really reasonable. So first of all, we choose the most efficient solution, so the cell with minimum cost. We deliver this route with this minimum cost a certain amount of chocolate. The next step, we once again choose the next minimum cost and deliver by this route the next part of batch of chocolate, and so on. It seems optimal, but it is not guaranteed to be optimal. Sometimes we find an optimal solution, but sometimes the solution is not optimal. And also, such a method, which is least cost method, it is an example of a class of methods which are known as greedy algorithms. So these algorithms, yes, they looks like optimal, so because they run local optimization. So first solution is local optimal. So the next solution is local optimal, but in general, when we consider the system as a whole, so the solution could not be optimal. Let's consider an example. The same case, and in this case, let's consider the cell with minimum cost. Obviously, this is the cell with the cost 1, and it is the first step. The delivery is once again is the minimum from supply and demand. So in this case it is 8, and supply now is 0, and we cannot deliver anymore to all the customers, and we correct our demand. Now it is 1. And also let's continue with this table, and the next minimum cost is 2. So and it is the second step. We deliver here the minimum from 11 and 5. The minimum is 5. So the first customer is satisfied, and now the second supplier we reduce from 11 to 6 the supply volume. The next step with minimum cost is this one, and it is the third step, and we deliver the minimum from 11 and 7, so the minimum is 7. Here 4 choco boxes remains, here is 0, and if this customer does not need any more chocolate, so we send a message to the second supplier 0. The next step, the minimum cost in the remaining table is 4, so it is the fourth step, and we deliver here the minimum from 6 and 9, and it is 6. So 0 is here, and so 0 is here, and we correct our demand, so from 9 to 3, and we continue with the remaining table. So minimum from 8 and 5 is 5, so it is the fifth step. So, and we deliver here minimum from 4 and 1, so we deliver here unit, we correct this demand, and we correct this supply, and the last step is here, so this is the step number 6, and we deliver 3 choco boxes here. Good. And this next question, the same as before, may we use least cost method for unbalanced problems? Yes, we may use this method for unbalanced problems, but at the end we will get a surplus for supply sides if we consider overproduction case, or unsatisfied demand if we consider the shortage case, but we may use the least cost method. And if we calculate now the transportation cost for this case, Z, it is Z2 because we consider the second method. So the same fashion, O times 7 plus and so on, O times 2. So, and as a result we will get 92, and I remind you that optimal solution is the one which brings the transportation cost of 89. So, and this is the evidence that least cost method does not guarantee optimality. In this case, least cost method brings the solution which brings the transportation cost which is bigger than the transportation cost for the optimal solution. And now let's consider the last heuristic method, which is known as Vogel approximation method. The idea is the following. For a row or column with maximum Vogel's fine, we fill the cell with minimum cost. Implementation. So we implement the Vogel approximation method only for estimation. Because it requires a bigger amount of calculations rather than the previous methods, and usually this approach is used for estimation of the solution. The algorithm is represented here on the slide, but I would like to show you the method, and you may just compare this method with this algorithm which is represented there and on the slide. And first of all, how to calculate Vogel's fines? Let us consider the first row in this table. So we consider the same example as before, and this first row is about the first supplier, and let us calculate the Vogel's fine. How to calculate the Vogel's fine? So first of all, we need to find the minimum cost in this row. The minimum one is 3. The next one, we need to find the next minimum cost in this row, the next minimum. So when we hide this column, what is the minimum cost in the first row? Obviously, this is 5. It means that Fogel finds for the first row is 5 minus 3. 5 minus 3, it is 2. The same way we consider the second row. The minimum cost is 2. The next minimum is 4. The difference is 2. The third row, the minimum cost is 1. The next minimum is 2. So the difference is 1. The same fashion continue with the column. So consider the first column. The minimum cost is 2. The next one, the next minimum is 6. The difference, 6 minus 2 is 4. For the second column, the minimum is 3, the next minimum is 4. 4 minus 3 is 1. For the next column, the minimum is 1, the next minimum is 5, doesn't matter which one. So the Vogel's find is 4. And for the last column, the minimum cost is 2, the next one is 3. So the next minimum. So and difference between 3 and 2 is 1. So, and it is the first step, and we consider such a border to mark the first step. And now we should find a maximum Fogel find. So according to our idea, we should find the maximum Fogel find, and the maximum is, as we can see here, 4, 4, and so on. So 4, it is the maximum Fogel find. So there are 2 4s in this case, and it doesn't matter which one to choose. I propose to take the first one, for instance. And it means that if this maximum Fogel find corresponds to the first column, it could be, for instance, the second row, it is possible. So in this case we choose the second row, but in this case it is the first column, and in the first column we should fill a cell with minimum cost. So what is the minimum cost here? It is 2, and it means that it is our first step, and we should deliver there. And we deliver once again the minimum from 5 and 11, and the answer is 5. And we correct our demand, so now it is 0, and supply, so now it is 6. And so the first customer does not need anymore. And it was the first step. Continue with the second step the same fashion. So now the first column disappears, and once again let us calculate Fogel finds. For the first row, the minimum is 3, the next minimum is 5. So once again, so Fogel find is 2. For the next row, minimum is 4, the next one is 5, the difference is 1. And for the last row, the minimum is 1, the next one is 2, so the difference is 1. And for the first column, no changes, so minimum is 3, the next one is 4, so once again 1. So no changes for the next column, so the Fogel find is 4, no changes for the last one, so the Fogel find is unit. So now let's consider what is the maximum value of the Fogel find. So the maximum value is 4. So it means that we choose this column and we choose the cell with minimum cost. It is this one, and it is the second step. We deliver there. How many? The minimum from 8 and 9. So we deliver there 8 choco boxes. Now we correct our supply volume, and this is 0 and 0 delivery to these customers, and we correct our demand volume. Now it is 1. It was the second step. Let us continue with the next one. For the first row, the minimum the minimum cost is 3. The next one is 5. no changes here too. For the next row, no changes, so the same Vogelfine. And we do not consider the last row because the supplier is empty now. And let's consider the column. The minimum value is now 4 because the last row disappears. And the minimum is 4, the next one is 8, so 4 it is the Vogelfine. So difference here is 5 minus 5, it is 0. So, for the last column, 9 minus 3, it is 6. And the maximum is 6. And it means that we choose the last column now and we choose the minimum cost. It is 3 and it is our third step. And we deliver here. So we deliver minimum from 11 and 7. So it means that we deliver 7 here. So the demand is fulfilled and here remains 4 units. And now we may write 0 here because demand of the last customer is met. And continue with the next step. Yes, too much calculations, and for this reason Vogel's approximation method usually used just for estimation, not to find a feasible solution, because it is too heavy for such a simple problem. So it is much more easier to use northwest element rather than the Vogel method to find a feasible solution. Okay, we continue. And now the Vogelfine here is 8 minus 5, it is 3. For this row, 5 minus 4, it is 1. And also we consider this column, the difference is 4, and for this column difference is 0. So the maximum volume is 4, and we deliver to the second column and we choose the minimum cost, and minimum cost is 4, and we put 4 here, and we deliver minimum from 6 and 9. So the minimum is 6. And now the remaining supply for the second supplier is 0, and for this reason we put 0 here because the supplier is empty. And we correct our demand volume, and now demand volume is 3. And we continue with the remaining table. So, and there are only 2 cells in the remaining table, and for this case we use the least cost method. So first of all we deliver there, and it is the step number 5, and we deliver their minimum from 4 and 1, and we deliver their obviously unit. So demand for this guy is met, and only 3 units remains here. And the last step, the step number 6, is here, and we deliver their 3 units of Choco boxes, 0, 0 here. And this is the result of the Vogelfine. And once again I may calculate the transportation cost for this case, and Z3 it will be once again it will be 92. And I remind you that minimum possible transportation cost is 89. And we may say that all these 3 methods which we discussed today, northwest element, least cost element approach, and Vogel's approximations method, all of them are heuristic solutions. So, and they are rather simple. So we found the solutions without computers, but we found that transportation cost for the northwest element was very big, 150. For the least cost method and Vogel's approximation method, so the solution brings the better transportation cost, and the difference with the optimal solution is rather small, but they are not optimal. The general idea is the following. Any heuristic method does not guarantee optimality, but it does not mean that they do not bring optimal solutions. So, is it possible that northwest elements bring the optimal solution, but least cost method and Vogel's approximations method not? Yes, it is possible. So in this case, northwest element is lucky. And the next question, is it possible that least cost method brings optimal solution, but northwest element and Vogel's approximation not? Yes, it is possible. So, and it is possible that only Vogel's approximation method brings an optimal solution, but the least cost method and northwest element not. Yes, it is possible. And the next question, it is possible that none of these methods brings optimal solution. Yes, it is also possible. So we can see this in our example. None of these three methods bring optimal solution. And for this sense, we say that heuristics methods are reasonable. That's it. Thank you.